Oh, that would be cool. Look, I can put their picture of me just so I can record everything. Huh. The only problem is it would be like hiding a little bit of the slides, so I guess I will not do that. Just stick with the standard thing. All right. Okay, so as you have noticed, I gave you eventually one more day for the project number 2 because there were some issues with the get BTS function, which turns out to be just in one of the toolboxes. So I guess you probably figured it out by now, I hope. Some of you struggled with that a little bit, which was not intentional. As you notice, there is no homework or project for this coming week because there's the fall break, so you might as well enjoy some last days of nice weather before it gets too cold. About the midterm, I was thinking if you would be okay doing it on October 29, as opposed to us previously saying like maybe 23rd or something like that. Might work a little bit better, the scheduling. I want to do a little bit of practice before, give you the practice problems and solutions, and I want to squeeze in one more homework. Sounds good. Okay, so let's just continue with rectangular matrices, how to solve systems of linear equations with rectangular matrices. It's a little bit more blurred than I would hope. Yeah. It's a little bit better, huh? And today I would like to make the point that it's very nicely understood, all these properties of general matrices, and especially their solutions of linear systems with rectangular matrices, are very nicely understood when you think in terms of subspaces. With every matrix, there are 4 very important subspaces called the fundamental subspaces. But I guess to be making any sense, I first need to properly talk about what are subspaces. So we will get there. So let me first start with what I ended before. I think before we were talking about the rank of a matrix, right? Do you remember how was the rank of a matrix defined? Now I'm talking about arbitrary. It's a real matrix, so no such thing as complex matrices, but it can be rectangular, any shape and form you can imagine. That includes also like the degenerate type of matrices, like 1 row or 1 column type of matrices. Fine, right? So all theory should still apply. So how was rank defined? This is sort of giving you a clue. Exactly. After I convert the matrix to reduced row echelon form, the number of pivot elements, that's the definition of the rank. There are different ways to define rank, but this is the one we had last lecture. Okay. And okay, here I was explaining that using elementary row operations, you can bring the matrix to reduced row echelon form. I think I said this before, so let me just show it quickly. The same thing you can do, or in an analogous way, you can do elementary column operations. And this way you can reduce it to reduced column echelon form. It's the same idea, just I apply the Gaussian elimination basically on the right. You could also look at it as applying Gaussian elimination on A transpose, by the way. That would be the same thing. And I think what we ended with was rank normal form, which basically means nothing but putting these two together. So doing Gaussian elimination both from the left, both on rows and on columns, okay? And if we do this, we can always reduce an arbitrary matrix to this form, where I have identity block. So the IR is a square R by R matrix, which is the identity matrix. And then I have some rectangular blocks of all zeros. And from this, of course, it's obvious to see that the rank of this matrix is R, right? That's the number of ones in the identity block there. Let me again remind you this GLM. What does it mean, the GLM? Maybe someone else can say it. That's sort of one reason why I covered the group theory, so I can simplify my notation. General linear group in m dimensions. That's absolutely correct. And what does it mean? If these guys are from GLM, it's not a lot you have to remember for the midterm, but something you do have to remember. so that we know, like this jargon, right? So who does remember that? By the way, in lieu, if you have some time, instead of the homework, what you can do is either work with the textbook or look at the lectures previously, especially if you missed some of the lectures. You can check it out on YouTube and go through it. You can actually play like with higher speed. I usually watch it like 1.5 speed, and it gets more funny. So if you don't remember this, like going over this again might help to refresh your memory. If you wanted to do something even more interesting, you can try to solve the 2D Laplace system. I don't think I will do a project on it eventually, but if you feel curious, you can just do it. I think you know everything, all you need. So okay, I digress. So what is GLM? GLM is, so what it means, it's a matrix group, right? And those are square m by m matrices which are invertible. Okay? So m was the number of rows of the matrix, n was the number of columns. So this one goes from the right, so it has to be n by n invertible, and this is m by n invertible. Okay? Okay. So I think I did not show this the last time, so let's discuss it now. What is important about the rank is that the rank is sort of characterizes the matrix in the following sense. It's invariant to multiplying the matrix from the right or from the left by an arbitrary invertible matrix. So let me try to say it again in more, hopefully more digestible form. If I multiply the matrix from the left or from the right with an invertible matrix, the rank doesn't change. Okay. So why is that? Let's take a look at it. So my original matrix can be converted to rank normal form by applying the elementary row operations from the left. If I concatenate all of them together, I get the matrix P, and it's gonna be square and invertible, right? I don't really have to say square if I say invertible. Invertible already implies square. But I just want to emphasize this squareness. A Q is also invertible. Now it's n by n, and those are the elementary column operations, right? Well, then let's say I take another matrix B, which I got from A by left multiplying it with V and right multiplying with W, where V and W, they are both invertible matrices, each of different dimensions. So I guess I'm proving at the same time from the left and from the right. You could also prove first from the left or from the right, but it's so simple I can just like lump it all together. Does it make sense? Okay. Well, then watch this. So, oh, by the way, what is the V inverse here? Or better said, what is the reduced row echelon form of V? Oh yeah, that's a great idea. To give you time to think about what is the reduced row echelon form of V and W. So I said it's invertible, right? That means it's square, right? So these matrices have particle or simple reduced row echelon form. I'm pretty sure I mentioned this on Monday. Well, because it's invertible, if you are solving a system of linear equations, you cannot have any free variables, right? So it means that the reduced row echelon form is going to be the maximal one. The number of pivots, the rank, is going to be, in this case, n, in this case, m. It's going to be full rank. And I don't have to differentiate between column and row rank because the number of rows and columns is the same. So this is just a long way of saying that the reduced row echelon form of V will be what? Identity. Same thing for W. Are you guessing it? Just shy to say it. So if I do the inverse, again, so if I actually write the reduced row echelon form, I would see that V can be split into the individual row transformation, the elementary row transformations, right? W can be split into elementary column transformations. If I do the inverse, I just invert the individual row transformations. Same here for the column transformations. I'm not going to write it in detail because I already did it a few times before, so I don't want to be showing you all the same stuff. And ultimately, you can write it like this. So again, P is just a concatenation of elementary row transformations. So this whole thing is just a bunch of elementary row transformations, or you can look at it as a chain of elementary row transformations. Here, a chain of elementary column transformations. And this basically means that the B matrix I can convert to the same rank normal form. And why that's true? Because if for B I plug in VAW, because these matrices are inverse, this is exactly equal to BAQ, so I must get an R here. Okay? So that's showing that if I multiply A from the left with V and from the right with W, as long as the V and W are invertible, that's what I need here to be able to take the inverse, I get the same rank normal form at the end of the day. And of course that implies that the rank is going to be the same, must be, right? Because the rank is just the number of ones in this matrix. Okay? So remember this, if somebody gives you a matrix, it can be absolutely arbitrary matrix, and if you multiply from the left or from the right with invertible matrix, the rank doesn't change. So that's sort of good to know. Okay, so we can, I promised you we will look into the concept of a vector subspace. So let me first refresh your memory on vector spaces. This vector subspace is essentially just a special type of a vector space. So remember there was this laundry list of properties, which I don't, this is okay, this is something I don't really expect you to remember because I probably wouldn't remember it myself. I think we had to actually learn this for our linear algebra exam and then be able to reproduce it and then forget it, but it's just like, yeah, that's a lot. But intuitively, you should know all these properties. If somebody tells you like a property like this, it just should not surprise you, right? Those are kind of like a natural requirements if you wanna think about it intuitively. But let me just give you the gist of it. So the vector space, to recap real quickly, is a set which is endowed with two key operations, the scalar multiplication and vector addition, okay? And this laundry list of properties says what properties all these operations must satisfy so we can talk about a vector space, right? And there are these properties like it's closed under addition of vectors, the addition of vectors is commutative and associative, and there is a zero vector, and there is a negative vector for each of them. And then the final 5 properties, that's about scalar multiplication, right? So again, it's closed. It doesn't matter the order, it's associative. It can distribute with respect to addition of scalars and with respect to addition of vectors. And there is one which doesn't do anything. So very quick recap of that. And why I am bringing this up is because I want to introduce the concept of a vector subspace. So maybe let me motivate it from what you have seen from the group theory, because it's sort of the same type of idea. Or maybe actually exactly the same idea. Different algebraic level, I guess. So in group theory, we talked about groups and subgroups, right? Remember that? If you remember what was a subgroup was essentially a subset of my set of elements of the group, which was a group by itself, okay? And the key thing there was that it was closed, right? If I take any two elements from the subgroup and I multiply them together using the group operation, I need to stay in the subgroup, right? I cannot like run out because then it would not be a proper subgroup. Same idea with vector subspaces. So the difference between groups and vector spaces is that in vector spaces we have these two operations. We have vector addition and scalar multiplication. And for to be able to talk about a vector subspace, so first of all I have to start with some vector space V, right? In our case we will be just dealing with the familiar R2n, or n is any number. I mean, no, maybe we will take a look at some different vector spaces, but the R2n is certainly the most important one. And a subspace, first of all, it must be a subset, right? And it must be a subset which is closed with respect to these two operations, the vector addition and scalar multiplication. So what it means closed means that if I take two vectors, so if I take any two vectors from the V prime, which is aspiring to be a subspace, then I sum them together, they must also be in V prime, okay? Same thing for multiplication by a scalar. So if I take any vector in V prime multiplied by any scalar, so I assume I have a vector space over R here, I must not run out from V prime, okay? And if these properties are satisfied, then we say that V prime is a vector subspace, and what it means that V prime is actually vector space by itself. So all these properties, they would apply for it because they applied in the original vector space V, and I restricted it in such a way that the closure properties hold, and all the other ones they still hold too. They basically, because they held in the space V to begin with. Okay, subspaces are very important, and sometimes they are not just like mathematically, but also because they can give you a nice intuitive understanding of things. So let's talk. Let's see some examples of subspaces. So let's look at R2 first. So can you just blurt out without thinking some subspaces? Give me the dumb examples, the trivial subspaces, right? If you remember in groups, we had the trivial subgroup examples. It's just a tiny bit different in vector spaces. So what subspaces do I have in R2? So what would be the trivial ones? R2, exactly. So the vector, the space itself, yep. People can argue that it's a dumb answer, but it's absolutely valid, right? So this, the other extreme case, so this was the one where it's the vector space itself, right? What is the other extreme case? Zero vector, correct. So I guess I could write it like this, right? Just a zero vector. I can't get away from the zero vector because the zero vector has to be there already from this property, right? Because if I take something multiplied by 0, then it says that 0 must be in the subspace. So every subspace must contain the zero vector. Okay, so what about some non-trivial subspaces in R2? So those are the two trivial ones. What are the non-trivial ones? So let me draw my favorite R2. So this is the x-axis, this is the y-axis. So anybody has an idea? Now you have to be more creative, right? Now you have to think how does it have to do with the dimension of the original space? Yes, I guess this means that it's so well. Okay, I will give you one simple but non-trivial example. So if I just pick the x-axis, that means that y equals 0, right? That clearly is a subspace, right? Because if I take any vector here, multiply by a scalar, it will still be there, right? 0 is there, that's cool. If I take two vectors on the x-axis and sum them together, well, they cannot run out of the x-axis, right? So that's totally a subspace, right? Can you think about another example? Yeah? X plus 1? X equals 1. So let's see. So that would be this one, right? This line here. Yep. Now, let's see. Is this a subspace? That's an interesting point. I was going to mention this later. There is an interesting catch with this. So there is one problem with it, right? Doesn't contain 0, yeah. So you could talk about it. This would be an affine subspace. Or affine subspace essentially means take a linear subspace or vector subspace and translate it away. So this would be a perfectly valid affine subspace of dimension 1, but it's not a vector subspace because vector subspace must contain 0. So if you wanted to create a vector subspace of a similar idea, you could do just this, right? You could just say x equals 0. I guess that's this guy, y equals 0 is this one, right? Indeed, perfect subspace, right? So what other possibilities do I have? Well, you don't have to pick just these two axes, right? You can just pick any, as long as it passes through the origin. Pick your favorite vector, v, and then just say that all alpha v for all real numbers, it's going to be a line passing through the origin, and that's a perfectly valid subspace. right? Everybody does see why is it a subspace? Yeah, that's, yeah.
So as long as it passes through the origin, the linear equations, or can it be also like, doesn't have to be linear, right? It can be.
No, it has to be linear. Yeah. Actually, sometimes the term used instead of vector subspace is linear subspace. So yeah, we are dealing with linear algebra, so this has to be linear. So yeah, so something like this would not qualify. It has to be straight lines passing through the origin. And now this completely characterizes subspaces in R2, by the way. So there are the trivial ones, and there are all lines passing through the origin. That's it. Now, if you allow yourself to go to affine spaces, then you can start translating them. But we won't need, at least not in this lecture and the following ones, we will not need the concept of affine subspaces. It might be useful in some other areas, but we will just deal with linear subspaces, okay? What about R3? So I'll skip the trivial ones. Again, there is this one still applies and the entire R3, right? Those are valid subspaces in R3. So R3 I could, I guess, draw like this, right? I have my axis X, Y, Z. Can you tell me how all the subspaces will look like? Yep.
Just the line that passes through 0, 0, 0.
Correct. So all lines in all possible directions, right? I can shoot a line, will be a subspace, right? But now I have more, obviously. You can probably guess it. Exactly. Planes pathing through the origin, right? Those are also perfectly fine subspaces. And that's it, right? So the lines have, we will get to formal definition of dimension in a little bit, but you can probably see that the lines are dimension 1. Oh, we could, so this one would be dimension 0, right? Because it doesn't really have any interesting vectors, just the 0 vector. Lines would have dimension 1. Planes would have dimension 2, and the entire space is dimension 3. Okay, so I think that's quite easy. I guess I have a summary of this discussion on this slide. I just wanted to make it more interactive rather than just giving you, just telling you. So here we are saying that the planes are subspaces. I guess one way you could look at it is that if you pick any two, to convince yourself that a plane indeed is a subspace, then you need to verify that the closure properties are true, right? But I guess it's sort of obvious that if you take any two vectors in the plane and add them together, you get another vector in the plane, right? Just really the idea of linearity, right? It cannot really be curved, right? Because the moment it left curved away from the plane, this would not be true. Okay, so this is just a summary for you of what we just talked about. So the key thing of a subspace, let me just summarize it once again, is that it's closed with respect to addition and scalar multiplication and forms its own vector space. All right, another important concept is that of span. It's quite simple. So if I give you a bunch of vectors, k vectors in n-dimensional linear space, the span is defined as the set of all vectors formed by taking their linear combination. So specifically, I pick arbitrary scalars, alpha 1 to alpha k, and that generates some vector v. And all these vectors for all possible choices of alpha 1, alpha 2 to alpha k, that's a span of this set of vectors. Okay, so again, one thing you also do want to remember. I think there's some other terminology too. I think I heard like terms like linear hull or vector subspace generated by these vectors. I guess I should have mentioned that it's fairly easy to see that the span is a vector subspace, right? That's why I'm introducing it in this context. So why is it a vector subspace? I think that's trivial, right? If I take one guy like this and another guy like this and add them together, then I will get like a third guy like this, right? If I multiply by a scalar, then just all these multiply by a scalar, but I'm allowing myself any scalars, so certainly that's a subspace, right? It's very easy to verify. that's span. The other fun thing you can do with subspaces is you can add them together. So this is interesting because we are essentially defining plus on subspaces. So imagine then x and y are subspaces of Rn, and we can sum them together and obtain a new subspace. Okay, I'll give you an example in a second, but first the definition. So the sum basically means you take all vectors from one subspace, all vectors from the other subspace, add them together, and what you get is the sum. And again, it's very easy to convince yourself that this indeed will be a subspace, right? Because if I pick one element in the sum, another element in the sum, and put them together, again will be in the sum, and the same thing for scalar multiple. So that's trivial. So how can you think about this? So for example, here is how the line and plane subspaces in R3. So let's think about an R3 example. Okay. Let's say I want to. So let's start like this. So what is the? Okay, let me write it nicer. Span of, I don't know, 1, 1, 0, for example. So what is this subspace in R3? That's a line, right? In this direction, right? What if I do the plus, meaning plus of subspaces, adding subspaces? So it's cool to think about it that way. I don't know, pick your favorite direction, 1, 0, minus 1. So this is this span of 1, 0, minus 1, just pick some random vector, doesn't really matter what you put there. This is another line, right, in different direction. That's the only thing that matters, that these directions actually are different, right? Point in different directions. And what do you think I will get by doing the sum of the subspaces? Plane, exactly. Plane generated by these two vectors, right? I guess I'm not sure if I should attempt drawing it because it might be a mess, but there is one, there's another one, then all together they generate some plane, and that's exactly the sum of the subspaces. The only case when I would not get a plane, in this construction, for example, if I was so unlucky and picked here a vector like this, right, 2, 2, 0, which is a vector that actually points in the same direction, so I would not get any plane, I would just get the same line back, because I'm not really adding anything new, I'm just adding the subspace to itself. Okay? There'll be a lot of concepts today. So subspaces can also be orthogonal. We talk about orthogonality of vectors, and we can be talking about orthogonality of entire subspaces. Okay. So what does it mean for two subspaces to be orthogonal? Well, that means that every vector from the first subspace from X must be orthogonal to every vector in Y. Okay. So if I take any X from X, any Y from Y, their dot product must be 0. I think I said I will be denoting it like this instead of the dot, right? So let's stick with that. So again, what does it mean graphically? So let's think about some examples in R2. So let me give you an example of, or can you give me an example of two orthogonal subspaces? I guess it's easy, right? I'll just do it. There's an x-axis and y-axis, right? That's what you came up with before. And they are certainly orthogonal, right? Pick a vector from here, pick a vector from here, let's go down, certainly orthogonal, right? Some more interesting example would be, well, pick some line like this. That's one subspace. And if I want an orthogonal, if I want another subspace which is orthogonal to it, so let's call this the x guy and orthogonal y, right? So they would be, all you need is two orthogonal vectors, and they would generate two orthogonal subspaces. What about in 3D? Some examples of orthogonal subspaces involving plane and line, right? You can imagine you have a plane, which is a 2D subspace in 3D, and if you take the line perpendicular to it, the line in the normal to the plane, that would be an example of orthogonal subspaces of different dimensions, right? Can everybody imagine it, or shall I attempt to act it? Okay, you got it. Yeah, some of these things you can sort of visualize, but I think it's more powerful to have your mental image rely on that rather than some drawings. It's definitely faster if you can just imagine it in your mind. Okay, so that was this. There's another term. So what is linear independence? So again, this is concerning a set of vectors, and you will see how all these things connect to the problem of studying the system of linear equations of rectangular matrices. So these all are basic linear algebra concepts that I will need to explain the four fundamental subspaces. So this concept, linear independence, is another very important thing. You probably already heard it somewhere, if not here. So these vectors, a bunch of vectors, k vectors in n-dimensional space, are linearly independent if the fact that I take a linear combination with some alphas and the linear combination goes to a zero vector implies that all the alphas must be zero. In other words, probably more palatable, I just basically read it now, a more palatable way to think about it is that the only linear combination of these vectors that gives me zero is the trivial one. All zeros, okay? So you know certainly if you pick all alphas equal zero, right, then you certainly get zero. But the point of this definition is that the vectors v1, v2, and so on to vk are linearly independent if the zeros, if the trivial linear combination that goes to zero is the only one. Okay? If there is a non-trivial linear combination that gives me a zero vector, then we say that these vectors are linearly dependent, actually. Right in here. So if the vectors are not linearly independent, we talk about linear dependence. So how can I say that the vectors are linearly dependent? There is an interesting, no, not really that interesting. So I will just call it LD. Well, basic fact that these vectors are linearly dependent if and only if there exists an index I such that one of the vectors I can be expressed as a linear combination of the remaining ones. So let me read it one more time. Then I'm saying that the vectors are linearly, so linear dependent means not linearly independent. They are not linearly independent, they are linearly dependent. Those are complementary notions, okay? And here I'm saying that vectors are linearly dependent if and only if one of them can be written as a linear combination of the other ones. Got it? So we need to now show that this is consistent with this definition. So how could we do that? Well, let's start from the fact that they are linearly dependent, okay? So that means they are not linearly independent, right? So what does it mean if they are not linearly independent? That means that there needs to be a sequence of scalars alpha 1, alpha 2 to alpha k, which is non-trivial and gives me gives me zero. So that means, so okay, so if we write it, if they are not linearly independent, they are linearly dependent, that means that there is a non-trivial linear combination. Let me write it like this, that alpha 1 v1 plus alpha k vk equals 0, okay? The non-trivial means that there is an I such that alpha I is non-zero, okay? Yep. So what I can do now is to just, well, yeah, I can divide by the alpha I, right? And if I do this, I get alpha 1 divided by alpha I, v1, plus somewhere here is alpha I, so I divide by alpha I, why not? I'll get 1, right? up to alpha k divided by alpha I vk. 0 divided by alpha I stays 0, obviously. So this is 1, right? And here we can see that indeed I can just put vi on the right hand side, right? And what I will get is that vi equals, so I can call this beta 1. I can call this beta k, right? This is just 1, so I don't really need this. And I can index it with j's going over all indices except for I. And this is beta j bj. Okay? So indeed, this is what the second bullet point says. Is it clear to everybody? So linear independence says that you cannot express any of the vectors as a linear combination of the other ones. If you can do that, we say that they are linearly dependent. Then they are not linearly independent, they are linearly dependent. That means that one of them, dependent because one of them is sort of dependent on others. That you can create it by taking a linear combination of the remaining ones. I guess that's why it's called dependent. That's sort of that. I guess another way of writing this would be, you could say that vi is in span of v1, vi minus 1, vi plus 1 up to vk, right? So I skip this guy and it's in the span of the remaining ones. Okay. So, how can we test whether, if I give you a bunch of vectors, and that might happen, for example, in the midterm, I will want you to determine whether the vectors are linearly dependent or independent. So how can we do that? Well, we can turn to our arsenal of matrix tricks. So what we can do is we can take all the vectors, assume that they are column vectors of some matrix. So we basically I take all my, so I'm testing a linear dependence, or let's say I'm testing linear independence of a bunch of vectors. They all must have the same dimension, by the way, right? That's what I said here, that they are all from Rn, right? So I can just say, well, they are column vectors, right? So I can just as well write a matrix of them, right? And call this matrix A, right? In checking linear independence amounts to checking whether the only solution of this homogeneous system of linear equations Ax equals 0 is the trivial one, right? And from what we talked about before, the trivial solution will be the only solution if and only if A has full column rank, right? So I want you to remind of this. So how did this work if I was solving the system of homogeneous linear equations? I converted it to reduced row echelon form. And if there were some free variables, then there were non-trivial solutions, right? Because for the free variables, I could pick non-zeros and get a non-trivial solution to it. If there were no free variables, if A had full column rank, then the trivial solution is the only one, okay? And this gives us an algorithm how we can test whether a set of vectors v1, v2 to vk is linearly independent. We just form the matrix, we run the Gaussian elimination, get a reduced row echelon form, and we simply check if there is a pivot in every column of the reduced row echelon form. If that's the case, we are independent. If that's not the case, we are linearly dependent. Yep. By the way, here you can notice one thing. Here is an interesting quick observation we can make. If I am in Rn vector space, can I have n plus 1 linearly independent vectors? A set of n plus 1 linearly independent vectors? That's not possible, right? Why is it not possible?
Because the basis is already the maximum number. I'm not good.
Basis I'm defining on the next slide, so let's not refer to the basis yet, even though I see where you are going with that. Well, if you just apply this construction, right, and we have n plus 1 vectors in n-dimensional space, what type of matrix do we get? We get this short fat type of matrix, right? It will have one more column than row, right? And there is no way this matrix could be full column rank, right? The best case that can happen is that there will be all ones, but the last column, there's no way I could squeeze in one here because I just run out of rows here, right? So there will be at least one free variable, so it means non-trivial solution will always exist. So if I give you n plus 1 vectors in Rn, you don't even have to be computing anything, you can just immediately tell me linearly dependent. Must be the case. Maybe you don't know what are the exact coefficients, such that non-trivial, what are the non-zero alphas, which give me 0 when I multiply the A matrix with it. But you can immediately say that they will be always linearly dependent. Okay? Okay, so the concept of basis. I think I talked about basis a little bit before, but we did not have the concept of linear independence. So now we can actually give like a formal definition of what the basis is. Before I was sort of referring to like informalish definition of a basis. So the idea of a basis is that it's a set of vectors such that, so first of all, we are talking about basis of a given vector space, okay? So basis of a vector space B. And a set of vectors is called a basis if the span of this set of vectors is the entire vector space B, and the set of vectors is linearly independent, okay? So there are two conditions on a set of vectors to be a basis. The first one is that it spans the entire vector space and the vectors are linearly independent. Okay, condition number 1, condition number 2. So what's the meaning of it? Well, the meaning is the condition number 1 says that if I take, that basically the basis is my coordinate frame of reference, if you want to rephrase it. Because means that if I take any vector in my space, in my vector space, I can write it as a linear combination of the basis vectors, right? I think we had this before. The condition number 2 requires that in addition to this, these vectors must not be redundant, essentially, right? That's what linear independence means, right? What if I allowed here to take linearly dependent vectors? It means that the combinations, the coordinates of each vector with respect to this so-called basis would not be unique, right? Because if I take linearly dependent vectors, then one of them is dependent on the others. One of them can be written as a linear combination of others, right? So that means I could as well take that vector out and get a smaller basis. So we don't want that. We want basis to have just the right number of vectors to be able to uniquely describe any vector in the vector space. And by describe, I mean give me coordinates for it. Okay, so again, the definition of a basis you absolutely must remember. And don't worry, as we'll be talking about this, it will become more and more natural, unless it is already. So one quick way how I can get a basis of Rn, and actually this characterizes all bases, is if I take an invertible matrix, I guess I could also write GLN, right, alternatively. Well, for, I think we discussed this before, right? For invertible matrix, the only solution of this homogeneous system of linear equations is the trivial one, right? What was the argument again? I said it earlier. I guess I'm just testing if you were paying attention. Well, because the reduced row echelon form of an invertible matrix is the identity, right? So it doesn't permit any free variables. So the solution is unique. So the trivial solution is, because it is a solution, is the only one. Okay, and because this is true, it means that the columns of A are linearly independent. Shall I repeat it? Or maybe shy. So yes, so the column vectors of any invertible matrix constitute a basis because they are linearly independent and they generate the entire space. Here is another important result, or I guess definition, and then we prove something that gives sense to the definition. I guess no way. This is a fact that will lead to the definition of dimension. Again, the formal definition of dimension. So the claim is that if I have some vector space, in this case I just said Rn, but you could just put any vector space there, and I have two sets of vectors which are both bases. Okay, I have one basis and another basis. So I claim that in this case, both bases must have the same number of vectors. You cannot have a smaller basis and a larger basis, right? That's really the idea of a basis. Let's see how we can prove it. Prove it by contradiction. So we will assume that one of them is actually larger. So let's assume that n is a basis with more vectors than, or S1 is a basis with more vectors than S2, that n is strictly larger than m. But S2 is supposed to be a basis, right? So what does that mean is that any vector in S1, each of these W's, I can write as a linear combination of the basis vectors in S2, as a linear combination of V's, right? There's a neat way to write it using matrix multiplication, because you see, if you look at these W1, W2, and so on to Wn as column vectors, and same here for the V's, that if this is true, if any of the W's I can write as a linear combination, they can just put all of them into a matrix, right? So this says that W1 is a linear combination of all the V's with these coefficients. Same thing for W2 with these coefficients, and so on for W2 with these coefficients. Again, I'm referring to the center of your brain for matrix multiplication. So this W matrix is the columns of the first basis. The V matrix are the V matrix stacks the column vectors on the second basis, and the A matrix is the matrix of linear coefficients that have to exist. Right? That's the property of a basis, that any vector can be expressed as a linear combination of the basis vectors. Okay. Well, but then this matrix is an m by n matrix, right? And I assume that n is strictly larger than m, right? So that's again the example of a short and fat matrix, right? It has more columns than rows, right? And this matrix must have, let's say I didn't define null space, yes, must have at least one free variable, right? Exactly the same argument as before. I just run out of pivots. There must be at least one column without a pivot element, right? That will be my free variable, and that means that I can find a non-trivial x, non-zero x, which gives me a x equals 0. Okay. Well, but if I did that, I can just multiply from the left with V. V is this matrix. Multiply with V. If I multiply 0 with V, I certainly get 0, still 0, right? Nothing changes there. But V times A, this is V, this is A. V times A is W, right? That's what we had here. That's how we defined A. But now we have a non-trivial x such that the linear combination of all the column vectors of W gives me 0. So that's a contradiction with the assumption that the columns of W were linearly independent. Okay? So this, if I should sum it up, this basically shows that if I take one basis and another basis, I cannot have different numbers of vectors in each of them, that n must be equal to m. Because if not, I can construct a contradiction with the definition of a basis. Okay? Wonder if I should give you some example to give it some more. You know what? Let's. I guess this fact, which I just proven, justifies the definition of the dimension, because the dimension of a vector space. Now this is the proper formal definition. Is the number of vectors in any basis. Number of vectors in a base. That's the dimension of the vector space. Yeah. And now, due to the previous property, you know that doesn't depend on the choice of the basis, because every basis must have the same number of vectors. So indeed, this is just a property of the vector space itself. So that's how we define dimension. So basis, like in 2D, we are already talking about these standard bases, right? E1 and E2. That's a perfectly fine basis. You can also choose this as a basis, right? They are certainly linearly independent. They generate the entire vector space. It's a perfectly fine basis. Later we'll be talking about orthonormal bases, in which case they need to look something like this. One vector and the other one needs to be orthogonal to it. Interesting thing about the dimension, actually, let me give you a slightly interesting example. Usually we are working here with just R2n vector spaces, but I think I told you already before that there are other important cases of vector spaces which are not R2n. So for example, if I take an interval of 0, 1, and let's say that I define polynomials on this interval. So ft equals at squared plus bt plus c, where my t goes from 0 to 1, okay? And we had this before, and I was saying that this is a perfectly valid example of a vector space, because I can just define sum of two polynomials, multiply polynomial by a scalar, and all the laundry list of properties of vector spaces is satisfied. So what do you think is the dimension of this vector space of polynomials on 0, 1? Or it could be the entire real line. Doesn't really matter, the 0, 1. I just wanted to make it sort of more concrete. Or easier to draw, I guess, not more concrete. A little bit more than that. So I guess let's think what type of functions are there, right? So there would be certainly constants, right? There would certainly be any linear functions, actually any affine functions, and there are quadratics, right? Something like this, right? Well, let's try to analyze this. So what do you think would be a basis? One simple example of a basis of this vector space. Actually, I said it a long time ago without having formally defined the basis. Yep. 1, 0, but right, I think what you were 1, 0, 0, I think you were referring to the values of the a and b and c coefficients. In that case, it's correct. So one basis could be this, right? 1t and t squared, right? So what I mean by this would be 1 would be this function, right? T would be this function, and t squared would be just a piece of the parabola, right? Sort of relatively easy to see that they are linearly independent, that because you cannot really create one of the functions by taking linear combinations of the other ones, and that they indeed, it's trivial that they generate the entire space, right? So the dimension is 3. Okay, I mean, sort of makes sense. You have ABC. The ABC, I should have probably said that they are just real coefficients. Okay. Now, where I'm going with this, you can imagine another vector space of functions on the same interval. You can imagine functions going from the interval to the real numbers, and say that they are continuous or even smooth. continuous is fine. So clearly this is also a vector space, and the space of polynomials is its subspace, right? Because polynomials are continuous functions, so, and this is a vector space by itself, so this is a subspace of it, right? And the tricky thing here is, what is the dimension of this space, of the big one, of the space of all continuous functions from interval 0, 1? That's a tricky question, because I think our definition wouldn't probably even work in that case. Does anybody dare to guess, I guess? Huh?
Like t to the, if it's t to the n, n in the.
What would be the n, right? Sorry, I can't hear you. I'm sorry, I still can't hear you.
You were saying that t to the n, well, that wouldn't work because you can have like sine.
Right. Imagine any function, right? Imagine like whatever crazy function, as long as it's a function, right? Doesn't have to even have any boundary conditions. So the thing is that this is indeed a vector space, but it's a vector space of infinite dimension. So that's the catch. So I guess my point here was that not all vector spaces have to have a finite dimension. This is an infinite dimension function space. And by the way, this is very important idea because it's sort of hard to work with infinite dimension vector spaces. But what we can do instead is we can take the interval from 0 to 1, subdivide it into some smaller pieces, and then say that we will use vector subspace of functions which are piecewise linear. So what I mean by piecewise linear is that they look like this, that they are, or piecewise affine, I guess, to be more accurate, that I just draw a line on each of these intervals. Okay? So piecewise linear functions on this interval. This would again be vector subspace. In this case, it would have a finite dimension, right? And this is basically the main idea of finite element method. To approximate infinite dimension function space with a finite dimension function space. Just wanted to give you this interesting application, so it's not just about the theory. And finite element method, that's like the key to lots of applications in mechanical engineering, graphics too, and whatnot. Okay, let's go back to matrices after a quick detour. So we will now finally get to the 4 fundamental subspaces of a rectangular matrix, which is a sort of a neat way to characterize what the matrix does if you interpret the matrix as a linear transformation, right? So there will be 4 subspaces, and starting with the column span, which is easy. They are all sort of easy. So what is a column span of a matrix? So I have a rectangular matrix, m by n. And the column span is nothing but the vector subspace formed by linear combinations of all the columns of A. So formally written, I pick any x, I do A times x, right? And you know that this is just taking a linear combination of all the columns of A. All the vectors this generates, they are called the column span. And it's easy to show that this is a subspace, right? Because if I have one vector y1, which looks like this, another vector y2 that has some other x2 here, if I add them together, I can just add x1 and x2 together, so certainly they will also be in this in the column span, right? The same way, if I multiply it by a scalar, I can as well multiply the x by a scalar, because multiplication by a is a linear transformation. So clearly CA is a vector subspace. of Rm. That's actually important, the Rm. M is the number of rows of my matrix. By the way, using this, I can already tell you an alternative definition of rank. Alternative equivalent definition of rank would be the dimension of the column space. Will probably make more sense after I explain all the spaces and how do they relate. So the null space, you probably heard this before, null space of a matrix. Have you? Have you not? So what is a null space? It's the set of all vectors which the matrix maps to 0. Okay, so it's set of all x's such that ax equals 0. And what I was referring to before were examples of matrices where this null space was trivial. It was just the trivial subspace, the one that contains only the 0 vector. That's, I guess, the dimension 0 of subspace. Again, it's easy to show that it indeed is a subspace, because if I take one vector which has this property, another vector that has this property, and I add them together, certainly ax1 plus ax2 will be 0 if ax1 and ax2 is 0. Same thing if I multiply by a scale, absolutely trivial, right? So that's obviously a subspace too. Now this time it's a subspace of R to n, so because it relates to the number of columns here, because I am multiplying with x. See that? This will be important further down. So the column span was a subspace of Rm, and the null space is a subspace of Rn, because my point really is rectangular matrices here. Oh yeah, I guess one application of the null space. Remember when I was talking about solutions of a rectangular system like this, ax equals b, I said that the way we do it is that we pick one xp, one particular solution that solves it, one xp that solves the system. And then I can write all possible solutions as the xp plus xs, where s were the special solutions. One way you can write it is that the special solutions are exactly the vectors in the null space. Remember this from the last lecture? So basically the fundamental subspaces of a matrix, they are more natural ways to talk about it. So I don't have to be talking about some specific column vectors and their combinations. Instead, you can basically abstract the fact that the subspace has some basis and all these things, and just think about the subspace, which is sort of comforting if you can think just about some plane and not worry what vectors exactly generate that plane. I guess that's really the main point of studying the subspaces, so you can think in terms of subspaces without worrying what vectors exactly generate them. So abstract that away. Okay, so is there anything else I want to mention? Probably not. So let's take a look how can we find the basis for the column span? So every matrix has some column span, like all linear combinations of ordered columns, and it's a linear subspace, so it must have some basis, right? And I wonder how can we find it here? And the way we do it is by reducing the matrix to the reduced row echelon form, that will be the R, by doing elementary row operations E. So again, here E is the invertible m by m matrix. Okay. So maybe let me illustrate this. So let's say that n is larger than m in this example. So this will be my E matrix, must be square, right, and invertible. And the R matrix is going to look something like this. So that's a reduced row echelon 1. So you know from the previous lecture that must have this staircase pattern. Like this, that could be like this, and there can be some zeros at the end of it, right? And if it's a reduced row echelon, it has this form that there is 1, and everywhere there are zeros. Then there is some non-zeros here, and this is another pivot column here. That would be another pivot column here, another one here. Just lucky I have plenty of pivot columns here. Then I have some values here, which I don't know what they are exactly. They could be zeros, they could be non-zeros. Here is another pivot column. And here are some numbers, which again, I don't know what exactly they are. So these are the pivot ones. By these dots, I mean some number, which can be 0, non-zero, can be whatever. And here, down here, they are all zeros. Okay, I don't know if zeros here. So this is my reduced row echelon matrix. Okay. And I want to use this to find the basis for the column span of the original matrix A. So the original matrix A, that's the product of the two, right? It has a dimension like this. So this is my input matrix. I'm interested in the column space of the matrix, and I wonder what's the basis of the column space. And the basis I can read from these two matrices. So the one thing you can realize is that if I call so in this case the rank would be 5, right, in the example I put there, but in general this would be the rank R. So F1 to FR here these vectors will exactly appear here, right? So my A1 will be exactly F1. Do you see that? And would be like 1, 2, 3, 4, 5. So it will be some A5, be A6, A7, 8, 9, 6, 5, 6, 7, 8, 9. That would be A10 somewhere around here. Okay. And what you can immediately see from matrix multiplication is that this A1 is nothing but F1, and the A5 is nothing but F2, and so on, right? Because this is what I get if I do the matrix multiplication, and that's because the pivot columns have this very simple form that they are all zeros up to the last one. Okay. And the point here is that if I take arbitrary column of A, it is a linear combination of these first R column vectors of E. Okay, do you see that? Because here are everywhere here are zeros, right? So whatever column of A I pick, if I'm lucky and pick one of these, one of the A1, A5, A6, A7, which correspond to the pivot columns, then I get exactly one of the columns of E. If I pick a different one, like for example the last one I get by multiplying this column with the matrix E, right? Well, it's still a linear combination of the first R columns. Okay, so any column of A is a linear combination of the first R vectors of E, the F1 to FR, which means that they exactly generate the column span. I could write it like this, that the span of F1 to FR is exactly the column space of A, right? And the beautiful thing is that E is an invertible matrix, so these vectors are linearly independent. They are the basis. So that's how you can find the basis for the column span of the matrix. Why that's useful, I think that will be more obvious when we get to the 4 fundamental subspaces picture. Just trust me for now that it will be useful. Okay, let me this is Well, I can certainly do the row span. I might be missing one slide I wanted to talk about, but most. So row span is an analogous concept to the column span. So the idea of a column span, we are taking linear combinations of columns. In row span, it means we'll be taking linear combinations of all rows, right? So one way I can write it, if I have a matrix that looks like this, let's stick with the short and fat ones. So if I take a row vector y, and my rows, I call them A1 to AM. If I take any vector y, then by taking these products YT, YTA for any y from Rm, I will get the row span. And again, it's easy to see that this is subspace of Rm in this case, right? Because, by the way, this gives me a row vector, right? Because I'm multiplying the matrix with the row vector from the left, it gives me a row vector back, right? So this would be some, I don't know, x or whatever. Okay. I can transpose this entire thing. If I transpose it, so I guess I should write there xt. I said that's I should write the transposes here too. I said it's polite to distinguish row vectors from column vectors, right? So I can say that y transpose A equals x transpose. I can transpose the entire equation. I can say equivalently that ATY is x. And that's basically saying nothing else than the row span of A is nothing but the column span of AT, right? I guess it's not very surprising because the transposition swaps the role of rows and columns, where rows will become columns. So if I'm looking at the row span as A, I can equivalently be looking at the column span of AT. Okay? And the final, I guess I'll just write it here. The fourth fundamental subspace is called the left null space. And that's a similar idea as the null space, but again applied from the left. So this would be all vectors y such that YTA equals 0. That would be the left null space. And it's actually nothing else but the null space of A transpose. Okay, I think I will need another lecture to finish up the discussion of the 4 fundamental subspaces, because there is many more important concepts which I need to discuss properly, and it's certainly not going to happen in a few minutes. So I think we can quit here unless you have some immediate questions. And if not, we will continue next week and enjoy the fall break.